And so welcome to AP Physics 1 exam review. This is going to be for our rotational motion exam and just the multiple choice portion of the review that I gave out in class for those of you that cannot be in extra help or just want to go over this again. So let's move into our first example here. All right, so our first example here, we have a record on a turntable is spinning and coming to rest. At time equals 0, the angular velocity of the record is 20 radians per second with a constant acceleration of -5 radians per second squared. What is the record's angular velocity at time equals 0.5 seconds? All right, so the first thing that really stands out to me here, or at least at the very end, is that I'm trying to find the record's angular velocity. This means that I'm going to be working with our kinematic equations here. I'm also given an initial velocity and an acceleration here in order to do this. So what I'm going to end up doing here is figure out what I've been given in the question. So at first, at time equals 0, which is my initial condition, I have an angular velocity of 20 radians per second. So that means that my initial velocity here is going to be 20 radians per second. I can write this out on the side over here. So omega naught is 20 radians per second. What I also have here is a constant angular acceleration of 5 radians per second squared. So I can put in here alpha is going to be -5 radians per second squared. I want to find what the angular velocity is at time equals 0.5 seconds, my bad, which is also better known then as the final velocity for this situation because we have a time. We then want to find the velocity at that time after we start at 0 seconds. So 0.500 seconds is my time, and I really just want to find omega, or my final angular velocity. All right, so what I'm going to do with this is look on my reference table and look for my angular kinematic equations and figure out an equation that is going to go directly with this. I see that I'm looking for my final velocity. I have a time. I have an angular acceleration. I'm going to fix alpha there, actually. It's bothering me. I have an angular acceleration and I have an initial angular velocity. So on the reference table, this can be known as my final angular velocity equation, kind of relating it to the final velocity equation all the way back from regular kinematics, or translational kinematics from the beginning of the year. So that equation is going to be that my final velocity, omega, is equal to omega naught plus alpha times time. All right, so from here, now I'm just going to plug in what I've been given and figure out my final angular velocity. So I am looking for omega. This is equal to my initial velocity, which is going to be 20 radians per second, plus my acceleration, which is -5 radians per second squared, times the time here. So -5 radians per second squared times my time, which is just 0.5 seconds. All right, so what I'm going to do here first is just multiply these two numbers together. So -5 times 0.5, plug it into my calculator, and I'm going to end up with -2.5. So I should have here now omega is equal to 20 radians per second, then minus 2.5, and now we should be in the same exact units because one of the seconds will end up canceling out. So I should have radians per second as well. So when I have here omega is equal to essentially 20 minus 2.5, just make sure so you don't make any mistakes, plug that into your calculator, and you're going to end up with your answer here of 17.5 radians per second. Oops. So that's going to be answer choice D here. All right, so let's move into our next example. All right, so example number 2, we have two wheels are fixed to each other and are free to rotate about a frictionless axis through their concentric centers. Four forces are exerted tangentially to the wheels. The magnitude of the net torque is. All right, so whenever it says net torque, net force, like early on in the year, this just means you're going to add up all the forces or the torques that are present. So we're going to use our torque equation here to get a net torque. So of course torque is going to be Fr sine theta. It looks like all these forces are going to be perpendicular to the wheel, so that means we're just worried about the force and the radius, or how the distance from the axis of rotation, essentially. All right, so what I'm going to do is set up my sum of all torques, and I'm going to end up labeling the forces on the diagram here as to what torque is what. So what I have here first, I'm going to write out the sum of all torques is equal to, the first force that I see here reading like left to right, I see a force that is going to be turning my wheel here. So I'm going to make this 1. So it's going to be F1 over here. And that is going to turn my wheel if it does actually end up turning based on this. Force is going to end up turning it is going to be counterclockwise. So that means it is going to be a positive torque. So that torque 1 that I'm going to call it, that is going to be a positive torque. So what we're going to have here, torque 1, that is positive. The next one that I see here is the torque that is 2F. So I'm going to make this 2 here. And based on the way that that torque is pointed, is going to actually turn my wheel clockwise. So if it's going to turn the wheel clockwise, that means that we end up having a negative torque. So torque 2 is going to be negative. Same thing now for torque number 3, the force directly next to it, that F, that is 2R away from the center there, is going to be F3 here. That is also going to turn my wheel in a clockwise direction. So that means that we are going to end up having a negative torque as well. So we're going to have negative torque 3. And for torque 4, the last one here, I'm going to put a 4 next to this. That force, which is 2R away from the axis of rotation, that is also going to end up being a negative torque. So what I'm going to end up having here is going to be another negative torque, and that is going to be torque 4. All right, so I should end up having 4 different torques. I'm trying to find the magnitude, so the sign at the end of the day, once we get the actual net torque, is not going to matter, but the sign is going to matter up until the actual final answer. So I'll explain that at the end. All right, so what I have here is essentially, again, all my forces are going to be perpendicular to the wheel here, so we're not going to be worried about sine theta. We're just going to plug in Fr for each of these. So torque 1, so the sum of all torques. Torque 1 here is the one that I have labeled there. It is a force. It is 2R away from the axis of rotation. So we have here just F times 2R. Minus torque 2. Torque 2 is 2F, and it is only 1R away from the axis of rotation at the center. So we have here 2F times R, minus another torque there, torque 3. That is only 1F, but again, it is then 2R away from the axis of rotation. So we have here force times 2R. And then our final torque there, again, is going to be just 1F, but it is, again, 2R away from the axis of rotation. So we have another F times 2R. All right, so let's do the algebra here, and this should be fairly quick to then sum together our like units or like terms here. So let me just do the math real quick. So we have the sum of all torques. Oops. For the sum of all torques, the first one, we're just going to have 2FR minus 2FR as well. Minus another 2F r, and then minus another 2fr. Alright, so we see here the first two will just cancel each other out, so 2fr minus 2fr is 0. Then when we add the last two up here, when we have the sum of all torques, we're going to have negative 2fr minus 2fr. That is going to give us a total net torque here of negative 4fr. And then when I look at what I'm trying to find here, I'm trying to find the magnitude of this. So just take the absolute value of this value. You're just looking for whatever the size of it is. You're not looking for the sign here in this situation. So my total net torque is going to be the magnitude of the net torque is going to be 4fr. So the answer is going to be answer choice D here. All right, so let's move into our next example. Let's move on to example number 3 here. We have a rubber band ball of mass m and radius r with a moment of inertia I of 2/5 mr squared. It rolls without slipping up an incline with an initial speed v. The ball reaches a maximum vertical height of, and what we have for the answer choices here are in terms of just variables, so we're not going to be dealing with any real numbers here, or any having to plug in anything essentially. Alright, so what we have here is a rubber band ball that is rolling up an incline. And it is rolling without slipping, so it's moving both translationally and rotationally at the same exact time. So I'm going to write out a little diagram here. So we're going to have an inclined plane. And we are going to have a ball at the bottom of that incline. It is going to then move up the incline and get to some max height at one point. So this is like our final position there. So just like when we had like blocks moving up inclines, the way to find the maximum vertical height is going to be through conservation of energy. But now there is going to be a little bit of a wrinkle added in because we have the object that is rotating. It's not just sliding up the incline like it would be with a block from earlier on in the year. So what I'm going to end up doing with this is just setting up my conservation of energy equation like I would before. And then we're just going to see what we have at the beginning and then what we're going to have at the ending point. So here, we know that conservation of energy is mechanical energy initial, so ME, is equal to mechanical energy final. And the equation for that is going to be potential energy initial plus kinetic energy initial is equal to potential energy final plus kinetic energy final. Alright, so what I have here initially, the ball is going to be on the ground. So that means when the ball is on the ground, potential energy is one of two things. It is either potential energy of a spin or is potential energy due to gravity. It doesn't say anything about a spin here, even though we have a rubber band ball. There's no spin in that situation, so it's not going to be potential energy due to that. And if you're on the ground, potential energy of gravity is mass times gravity times height. So that height is going to end up being 0. So we have no potential energy at all in the beginning of the situation. As for kinetic energy, it tells us that we are rolling without slipping up the incline with an initial speed v. That means we will have kinetic energy. When it says that it rolls without slipping, it means that it's continuously rotating and moving translationally. So we're going to have two types of kinetic energy here initially, which combine to be our total kinetic energy. So and it's going to be the same exact mass for this. So it's not like with the Pauli questions where it has a separate mass and there's two different kinetic energies. This is just the kinetic energies combined for this one object. So what I have here first is just 1/2 mv squared, our translational kinetic energy. We can then add this to the kinetic energy of the rotation as well, which is going to be 1/2. The rotational analog for mass is the moment of inertia I, and the rotational analog for velocity is just angular velocity, which is omega, and that is squared. Alright, so we're going to set this equal to the other part here. So afterwards, when we get to a maximum vertical height on a ramp, when we're throwing an object upwards, we always have we should have a condition of the object coming to rest when it gets to that max height. So if an object comes to rest what does that mean then for our energies? When we get to a max height, we're gaining height. So obviously, we're going to then have potential energy because potential energy due to gravity, because the potential energy due to gravity is mass times gravity times the height. So when we have some height, that means we do have that. So we have mgh here. But do we have any kinetic energy? Again, once we get to a max height, we should be at rest and we shouldn't be rotating anymore either. We should be at rest in all situations, both rotationally and translationally. So we should have no kinetic energy at that point at all. So this is going to end up being 0. All right, so we should have 1/2 mv squared plus 1/2 moment of inertia times omega squared is equal to mgh. One problem with this though, we do not have the angular velocity, and in our answer choices we have translational velocity v. So what I'm going to do with this is actually make my moment, not my moment of inertia, my rotational kinetic energy. We are going to make our angular velocity there into translational coordinates. And just like when we want to go from rotational into a translational velocity, which is v equals omega r, we can then make omega equal the translational velocity over the distance from the axis of rotation. So let's divide out r from both sides in order to do that, and we get that omega equals v over r. So we can then go plug that into our equation, and we can also plug in our moment of inertia from the first from our prompt here. So we have here 1/2 mv squared. We can leave that as is, no changes there. Plus 1/2 moment of inertia times omega squared. Again, if you're asking yourself why I'm doing this to make the omega into translational, the reason is we don't have what that omega is, so it is easier to make it into a translational coordinate than to try and have then multiple unknowns here. So we're trying to find h, we wouldn't know omega either. So to do this is going to make our life a lot easier. All right, so from here we have 1/2. The moment of inertia is given to us in the problem as 2/5 the mass of the object, and we keep that as m because it's the same mass moving both translationally and rotationally, and that is r squared. What I'm going to do to make my life a tiny little bit easier here, and this will make sense in a moment, when I plug in for omega squared, I'm going to make both my things squared here already. So I'm going to have here v squared over r squared. Then that is equal to mass times gravity times h. All right, so you should see a couple of things that jump out at you right away that you can now cancel out. I have one unit here, or one variable that is in each of the terms, and you should see that right away, and that is going to be my mass. So my mass will end up canceling out. So what I can do here is just cross out the mass in each of these terms. There's another thing that I can end up canceling out that only appears in one term, and that is my distance from the axis of rotation, r squared here. So r squared is on top, r squared is on the bottom, so these can end up canceling out. All right, so now I should be able to go forward with this. So I should have 1/2 v squared. Let me fix that. Should have 1/2 v squared plus 1/2 times 2/5. I'm going to make that into 2/10, and again, that will make sense in a second as to why I didn't just make that into 1/5. 2/10 v squared is then equal to gh. So my ultimate goal here is to end up getting h by itself on the right side of the equation, and then have my expression on the left side. So what I'm going to have to do on the left side first is just combine like terms. So I have 1/2 v squared plus 2/10 v squared. So in order to combine these fractions, what I'm going to have to do is, or I can make them into decimals, but my answers are all in fractions. What I'm going to have to do is get a common denominator. So I have here 2/10 for one of them, and I have 1/2. 1/2 should be a fairly easy changeover into over 10, and that is then going to be 5/10. So I have 5/10 v squared plus 2/10 v squared is equal to gh. All right, so let's move this over here for a second. All right, so 5 over 10 plus 2 over 10 is going to give me 7 over 10 v squared is then equal to g times h. So again, I'm trying to find what my maximum height is. So my last step here is to divide out g from h because it is being multiplied to it. Again, in any algebraic situation, you want to do the opposite of what is happening in order to get the object by itself. So I'm trying to get my height by itself on the right side. It is currently being multiplied to g. So in order to get it by itself, I must divide it out from both sides. So let's divide this out. This will cancel. G will go over here. And a better way to end up writing this is 7 times v squared over 10 times g is equal to my height h. So that is going to be my answer choice there, D. So we're going to get answer choice D when you do all the work for this question. So let's move into questions 4 and 5. All right, so questions 4 and 5 go hand in hand, so that's why I put them on the same exact slide. We have an ice skater that is performing a fast spin by pulling her outstretched arms down and close to her body. So if you've ever seen this before, I did this example in class with the textbooks on the chair. Spinning around first, I had the textbooks close to my body. I then pulled my arms out and I slowed down significantly. Then when I pulled my arms in, I sped up. The reason for this is the conservation of angular momentum. All right, so 4 is dealing with that. So what we have here, what happens to an angular momentum with respect to the axis of rotation? All right, so we should have a conservation of angular momentum because what is happening, and I guess I can make a tiny little diagram for this, so I'll make a stick figure. So what is happening here when you have your ice skater is when their arms are fully out, you are going to have a greater moment of inertia because the arms are further away from the axis of rotation, and you are then going to slow down. So momentum, or angular momentum, is L equals moment of inertia times omega. So in order to then keep this value conserved, then as my arms come in, so what I'm going to do here, I'm going to show the arms are inside, I guess. It's much smaller. In order to keep momentum then conserved, what is going to happen is my moment of inertia, I, is going to go down, but then my omega has to go up in order to conserve this angular momentum. So you've seen this before with ice skaters. They had to do the demonstration in class. If you've happened to come across this from another physics class, your teacher should have done a demonstration kind of like this, or they may have a better mechanism in order to do it. So they may have had students feel the sensation as well. So as you bring your arms in, you actually got faster when you spin, and as you pulled your arms out, you got much slower. And this is all due to the conservation of angular momentum. So we should have here that answer choice C is going to be my answer. All right, so as an ice skater performs a fast spin by pulling her arms outstretched down close to her body, so this is the same scenario. What happens to her kinetic energy? So unlike conservation of momentum, just like when we had collisions back in the regular momentum unit, momentum was always conserved. Energy is not always conserved. So the reason why in this situation, I'm going to explain why energy is not going to end up being conserved. So unlike here with conservation of momentum, energy is not going to end up being conserved because even though she speeds up to conserve her momentum, when we look at the kinetic energy equation, what's going to end up happening even as you speed up, your moment of inertia is going to go down, but your speed is squared. So essentially what's going to end up happening is your velocity is going to increase more than your moment of inertia is going to end up decreasing. So your kinetic energy is not going to end up actually being conserved because the equation for this is just K equals 1/2 I omega squared. Since that omega is squared, even though my moment of inertia is going to go down, my angular velocity is going to go up at a greater rate. So my kinetic energy is not going to actually be the same. So if for this situation, it should increase. So I should get answer choice A here for number 5. All right, again for that, because of the fact of the matter, even though my moment of inertia is going down, my velocity is going up. That velocity is a squared factor, so that means that that is going to go up at a greater rate than the moment of inertia is going down. So my kinetic energy is not going to end up being conserved there. And since she is getting faster or whoever it is, the ice skater is getting faster as they move their arms closer to their body, they are going to continue to speed up, so the kinetic energy should increase. All right, so let's move into number 6. All right, so number 6, we have a bicycle wheel of radius r rolls with a constant angular velocity on a horizontal surface without slipping. Which of the following is the right formula for the velocity of the center of mass? So this is essentially saying what is the velocity for the translational velocity, and we just did this on one of the previous questions to convert from angular into translational. So our answer choices here are v equals the r times omega. We have v equals r over omega, v equals omega over r, or v equals omega squared times r. So if I just want to find what the translational velocity here, the velocity of the center of mass, that's just going to be r times omega. We've been doing this since pretty much the beginning of the unit, so it might be written out like this, omega times r. You might be more used to it written out like that, but it's going to be the same exact answer choice. Answer choice A here should end up being your answer. So let's move into our next example. Let's move into example number 7 here. We have an experiment is performed in a physics class where 3 objects, an empty can, a D battery, a marble, roll down an incline of height h without slipping. A box slides down an adjacent frictionless incline of the same height. Which of the 4 objects reaches the bottom of their inclined plane first? So this is something that you might have seen. We did this in class with 2 different moments of inertia, but not necessarily like this. But there is a similar idea here. So what we have for our first 3 objects are all objects that can roll. A D battery can come as flat as well, but this is a circular D battery, obviously, because it says that it is rolling without slipping. An empty can is obviously more like a cylinder. A marble is going to be more like a sphere. So that's like a hollow cylinder would be the empty can, kind of. The D battery would just be a solid cylinder, and then the marble would be like a sphere. They all roll down the incline height h without slipping. So all of those 3 objects, they're not going to really matter. It doesn't give you what the moments of inertia are. You might have memorized them from class, but you're not going to really have to worry about it. So you have a box that slides down an adjacent frictionless inclined plane of the same height. So with the box has one thing going for it that the rest of the objects do not. It is only moving translationally. So all it has to do is convert from potential energy into translational kinetic energy. This means it's going to have a greater velocity as it goes down the plane. It is also then going to have a greater acceleration as it goes down the plane because it's not worried about friction doing anything. With any of the objects that have to roll and move translationally at the same exact time, that means that there has to be a force of friction creating some kind of torque in order to do that. So that will actually slow down or change the angular velocity of the object. So that means it's going to have less acceleration than the block. So you can test this at home if you have, say, maybe an ice block versus a can. The ice block should easily make it to the ground first if you have some kind of incline, or if you have, say, an object. If you have like a box as well, and maybe you have some WD-40 or something like that in order to make it frictionless, or try your best to make it frictionless, sit them off both at the same exact time, and you're actually going to see that the box is going to reach the ground first. This is again because it only goes from gravitational potential energy then into translational kinetic energy, so it's going to be both faster at the bottom, and with all the forces, it doesn't have that frictional force working against it, so it's going to have a greater acceleration moving downwards as well. So it is going to be the box. So answer choice D should get to the bottom of the inclined plane first. All right, so let's move into our final example. All right, so moving into our final example here, we have the system below rotates with an angular velocity omega. If the mass of the rod supports is negligible, what is the ratio of the angular momentum of the two upper spheres to the two lower spheres? All right, so what I'm going to do here with these objects, even though we're given spheres, what is happening here is that they are rotating at the end of arms or rod supports. That really means that they are going to be treated as point particles and not going to be given their regular moment of inertia, because the spheres are actually not rotating, they're just on the rods, and that whole system is rotating as one thing. So what we're going to do here, we're trying to find the ratio of the angular momentum. And what is angular momentum? That is L is equal to I omega. So just like with regular momentum, which is P equals mv, we have here L for angular momentum. I, of course, is the rotational equivalent to mass, and then omega there is going to be the rotational equivalent to velocity. All right, so now what I'm going to do with this is just show one last thing here. Like I said earlier, these are going to be treated as point particles, these masses, because they're not rotating themselves. They are rotating on the rods, essentially. If you can see like how it's spinning with the arrow there. So what is going to happen with these moments of inertia? A point particle, its moment of inertia is going to be just mass times the radius squared, or big M r squared as well. Same exact thing. All right, so let's start off here. Let me just label these. The top one I'm going to make angular momentum 1, and the bottom one I'm going to make angular momentum 2. So the first one we are going to work with is just L subscript 1. So that moment of inertia is going to end up being, we're going to have two of them because we have two masses on the ends of the rods here. So I'm going to have moment of inertia 1 plus moment of inertia 2 times omega. They're both going at the same exact speed. And then I'm going to plug in my moments of inertia here. So I have L1 again. The moment of inertia, they both have the same mass. This is going to be m times 2L. That is how far I am from the axis of rotation. So 2L, that is raised to the second power, plus the same exact thing, because the mass is the same distance. So m times 2L raised to the second power. This is all, again, multiplied by omega. All right, so continuing with the algebra here. M times 2L squared. A little bit of algebra is really just going to give us the mass, or I'm just going to do the math as well. So we have 4 m times L squared plus 4 mL squared. And again, that's going to come from just 2L squared. So 2 squared is 4. Bring that to the front. L squared is L squared. So that's going to be the same exact one for both of these point particles times omega again. And then finally, just combining all of these, I'm going to end up with 8m L squared times omega. All right, so L2. Similar idea here. So let me put this over here. We know again that is IW. So this moment of inertia is going to be two of these again. So I1 plus I2 times omega here. Again, it's the same exact angular speed or angular velocity. The main difference here is now we're going to have different masses and different distances from the axis of rotation. So we have here that L2 is going to be equal to our moments of inertia again. We are going to plug these in. I have now the mass, which is 2m. Again, these are the moments of inertia for a point particle, because these objects are not rotating themselves, they're rotating on these rods. So the sphere is not like rotating essentially. So that is 2m times L squared plus again 2m L squared. This is all multiplied by omega. Let me fix that. Now going further with the algebra here, we have 2ml squared. That is really just, again, 2ml squared. So let me just show the work here. So 2ml squared plus 2ml squared times omega. If we go one step further, adding these all together, L2 is going to end up equaling now 4ml squared all times omega. So now that we have both our not moments of inertia, we have both our angular momentums, what I have to do here is now just find the ratio. So what ratio am I looking for? I'm trying to find the ratio of the two upper spheres to the two lower spheres. So the two upper spheres we made as 1, the two lower spheres we made as momentum 2. So momentum 1 we found as 8ml squared times omega. And then momentum 2 we found as 4ml squared times omega. If you divide those two numbers, you're going to end up with 2 over 1. So we should get an answer here of 2 to 1. So we should have answer choice C. So let me just show that. If you do the math here, 8ml squared times omega over 4ml squared times omega, which is L1 over L2. You do all the math here. This cancels, this cancels, this cancels. 8 over 4 is 2 over 1, and that is L1 over L2 as we denoted. So that is going to be a 2 to 1. And again, to make sure we are correct, there's a 2 upper spheres to the 2 lower spheres. So 2 to 1 should be our ratio. That is answer choice C. All right, so this is all the multiple choice review that I gave out today. I will post the part 2s and FRQ tomorrow, so you should be able to go over this tomorrow when you go through this stuff, and then you should have that directly afterwards for the exam later this week. All right, so I hope this was helpful, and see you guys in class.